Assalamualaikum warahmatullahi wabarakatuh and hi to everyone. We are going to learn chapter 6 bonding theories of coordination compounds. Actually there are three types. So we are going to learn for the first type, valence bond theory. Valence bond theory actually is one of the earliest theory and this is proposed by Linus Pauling and John C. Slater. This theory is used to explain the hybridization, geometry and magnetic behavior of the metal complexes. Here are some points about this valence bond theory that we should know. So the first is central metal ion in the complex has a number of empty orbitals for the formation of coordinate covalent bonds with the ligand. So the number of empty orbitals available for the bonding should be equal to the coordination number of the central metal ion. The next point is hybrid orbitals are described according to the geometry of the complex. Next, about the ligand. So as we know that each ligand has at least a pair of electrons. The next point is about the coordinate covalent bond between ligand and metal. How this bond occur. So actually the bond forms when empty hybrid orbitals of the metal ion overlap with the filled sigma orbitals of the ligand. Alright, the next key point is d orbital involved in the hybridization could be inner d orbitals or outer d orbitals. And the last point is non-bonding electrons on metal ion or atom occupy the inner d orbitals, do not participate in hybridization. Alright, so what we can see from this table shows us the relation between coordination number, hybrid and also the geometry of the complex. So for this course, we will focus on coordination number 4, which has two different hybrid orbitals and also come up with different geometry. And the next is coordination number 6. Also, we can see here two different kinds of hybrid orbitals but end up with same geometry of the complex. There are two types of magnetic properties for transition metals, which are paramagnetic and diamagnetic. Theoretically, we will get this information from the electron configurations. Alright, here I show you the first series of transition metals, which is scandium until zinc here. And then this is also, we can see the filling of electrons in 3D orbitals. For example, scandium, we can see 1 unpaired electron, titanium, 2 unpaired electrons, and so on. So, if the electron configurations result in unpaired electrons, for example, here we can see scandium until nickel have unpaired electrons. It means that these atoms will have a net magnetic field, and this is called as paramagnetism. However, if the electron configurations result in all paired electrons, for example, here we can see copper and zinc. So, all paired electrons in 3D orbitals. So, it means that these two atoms will have no magnetic field, and this is called as dimagnetism. Actually, magnetic properties can be proved from the experiment. So that's why I have shared a video from the YouTube about this experiment. So please look at the video and try to understand the explanation, the discussion about this experiment. Alright, so what is magnetic susceptibility? So this is actually the measures of how much a material will be magnetized in an applied magnetic field, and this is caused by interactions of electrons and nuclei with the externally applied magnetic field. So here you can see the formula, the relations between magnetic susceptibility and magnetization, and also the magnetic field. And this is magnetic susceptibility. Actually, we will get the magnitude from the experiment. Alright, another thing is magnetic moment. So the number of unpaired electrons on a given metal ion or metal atom actually can be used to determine the magnetic moment. So it means that the magnetic moment is the result of both spin and orbital contributions of unpaired electron density. So here you can see the formula how to get the value of magnetic moment. So this is the formula, involve orbital quantum number and spin. However, we assume that the orbital quantum is very small, so that's why we can simplify the formula like this. And we know that the spin is referred to the unpaired electron, so that's why again we can simplify the formula like this. So if we know that the transition metal has one unpaired electron, so we substitute the value in this formula and we end up with this value, 1.73 bm. This is the value of magnetic moment. Bm actually is the unit of the magnetic moment and is known as Bohr magnetons. Alright, so this is petrochemical series that consists of ligands arranged in order of increasing field strength of the ligand. So what you can see here on your left is the weak field ligands, iodide, bromide, sulfide, and on your right is the strong field ligands, cyanide and carbonyl. Theoretically, a strong ligand can change the configuration of the central metal ion or atom by causing force pairing, which is against the Hund's rule. So for example, here we look at the cobalt-3. So what you can see here, electrons, there are 6 electrons in 3D orbitals, and we can see here 4 unpaired electrons here. 1, 2, 3, 4. Alright, so because the cyanide ligand attached to the cobalt, and we refer to spectrochemical series, cyanide is strong field ligand. So that's why cyanide can force pairing of electrons, which is against the Hund's rule. So what we can see here, the result is all paired electrons and no unpaired electrons. So, however, a weak ligand cannot change the configuration of central metal atom or ion. Alright, let's look at this example. There are two complex ions and you are given the magnetic properties for both complex ions. Nickel tetrachloro is paramagnetic. So what we know is paramagnetic means nickel central metal has unpaired electrons. So how many? So we look at the magnetic moment here. 2.83 bm Bohr magnetons. It means that nickel as a central metal has 2 unpaired electrons. Alright, so we go for the next complex ion, which is nickel tetracyano. is dimagnetic. Dimagnetic means nickel central metal has no unpaired electron. So we look at the magnetic moment. The value is 0 here. So prove that this is dimagnetic complex. Then we look at the formula for both complex ion. As what we can see here, they have same coordination number, which is 4. So as we know that complex that have coordination number 4 can be 2 geometry shape. It could be tetrahedral or square planar. So that's why these questions you need to show the hybrid orbitals and suggest the structure, which is the geometry shape of each complex based on valence bond theory. Alright, the first step is we need to find out the oxidation number of nickel. So here, nickel plus 4 equal to minus 2, and we will get nickel plus 2 oxidation number. So that's why here the next step is we need to find out the electron configuration for nickel 2. And then we look at the number of electrons in 3D orbital here. There are 8 electrons. So refer to the Hans rule, we need to fill in electrons in 3D orbitals. 1, 2, 3, 4, 5, 6, 7, and 8. And then what we can see here, these 2 electrons remain unpaired. So this is proved by the magnitude of the magnetic moment, 2.83 bm. Next, let's look at the ligand. There are 4 chloro. So we know that each chloro donates 2 electrons. So if 4 chloro means that there are 8 electrons will be donated to the nickel. 4 chloro donates 8 electrons to the nickel. Alright, and then valence bond theory said that the bond between metal and ligand occurs when empty orbitals from the metal overlap with the filled orbitals from the ligand. So, because ligand donates 8 electrons, should be this is empty orbitals from the metal. So the 8 electrons will be here. 1, 2, 3, 4, 5, 6, 7, 8. These 8 electrons comes from 4 chloroligands. So what we can see here, what is the hybrid here? The hybrid is sp3. So the valence bond theory assume that if the hybrid orbital is sp3, the geometry, the structure of the complex should be tetrahedral. Alright, now we look at the second complex ion, nickel tetracyano. And again, we need to determine the oxidation number of nickel. So nickel plus 4 multiplied by minus 1 equal to minus 2, and we get the nickel as plus 2. So for the nickel 2, we write the electron configuration and we look at the number of electrons in 3D orbitals, there are 8 electrons. So we need to fill in the electrons in the 3D orbitals by refer to the Hans rule. 1, 2, 3, 4, 5, 6, 7, and 8. Alright, now we look at the magnetic moment of the complex. They say that this complex is 0 magnetic moment, diamagnetic. So it means that this complex should be no unpaired electron. So that's why the filling of electrons we need to change. It will be like this. So what you can see here, all electrons paired. Due to this complex, the nickel bind with 4 cyanide ion. So as we know that each cyanide donate 2 electrons. So if 4 cyanide means 8 electrons. So nickel should provide 4 orbitals. So here the electrons will overlap here. 1, 2, 3, 4, 5, 6, 7, and 8. So these 8 electrons comes from 4 cyanide, and as what we can see here, the hybrid for this one will be DsP2. Okay, so that's why this is the hybrid orbitals, and valence bond theory assume that the geometry should be square planar. In conclusion, valence bond theory assumes that if the complex has 4 coordination number and it is paramagnetic, the hybrid should be sp3 and the geometry is tetrahedral. However, if the magnetic property is diamagnetic, the hybrid is dsp2 and the geometry should be square planar.